Welcome to Astro Odyssey. Explore the universe. For most of human history, the universe appeared calm, eternal, and unchanging. Night after night, the same stars traced the same paths across the sky, giving the illusion of a cosmos locked in place. Civilizations rose and fell beneath this steady celestial backdrop, and for thousands of years the heavens seemed immune to time itself. Even as astronomy evolved from naked-eye observations to telescopes capable of peering deep into space, the underlying assumption remained the same. The universe was static. It existed. It endured. And it always had. This belief was not born of ignorance, but of observation. When astronomers looked outward, they saw stars fixed in position relative to one another. Galaxies, then thought to be island universes or mysterious nebulas, showed no obvious signs of motion across the sky. Everything suggested permanence. And so, when early 20th century scientists began constructing mathematical models of the universe, they naturally assumed stability as a starting point. The idea that the universe itself could be growing, stretching, or changing in size was not just unexpected, it seemed absurd. Even Albert Einstein, whose theory of general relativity would revolutionize physics, was uncomfortable with the implications of his own equations. When he realized that gravity, as described by his theory, would cause the universe to either collapse inward or expand outward, he resisted the conclusion. To preserve the notion of a static cosmos, Einstein introduced a mathematical adjustment known as the cosmological constant, a term designed to counteract gravity and hold the universe in place. It was an elegant solution to a problem he believed must exist, because the alternative dynamic universe felt too radical. But the universe had other plans. In the decades that followed, increasingly powerful telescopes revealed a reality far stranger than anyone had imagined. Astronomers discovered that the faint smudges of light scattered across the sky were not clouds of gas within our own galaxy, but entire galaxies of their own, each containing billions or even trillions of stars. More astonishing still, these galaxies were not sitting still. They were moving. And not just moving randomly, but moving away from us in every direction. This realization marked a turning point in human understanding. The universe was not static. It was expanding. The discovery of cosmic expansion transformed cosmology overnight. Space itself was stretching, carrying galaxies along with it like raisins embedded in rising dough. The farther away a galaxy was, the faster it appeared to be receding. This wasn't because Earth occupied a special central position, but because expansion was happening everywhere at once. Every point in the universe could claim to be the center, and none of them truly were. For a time, this revelation felt like the end of the mystery. If the universe was expanding, then by running the cosmic clock backward, scientists could infer that it must once have been smaller, hotter, and denser. This line of reasoning led to the theory of the Big Bang, a moment when space, time, matter, and energy, as we know them, began. The expansion rate of the universe became a crucial number, a cosmic speedometer that could tell us the age, size, and fate of everything that exists. And for decades, it seemed like cosmologists were closing in on the answer. As measurements improved, a consensus emerged around a value describing how fast the universe is expanding today. This number, known as the Hubble Constant, became a cornerstone of modern cosmology. With it, scientists could estimate how old the universe was, how quickly galaxies were separating, and how cosmic structures evolved over billions of years. The universe, once mysterious and unknowable, appeared to be yielding its secrets to careful observation and precise mathematics. Then came another surprise. In the late 1990s, astronomers studying distant supernova discovered that the expansion of the universe was not slowing down, as gravity should have caused, but speeding up. Some unknown force was overpowering gravity on the largest scales, pushing galaxies apart faster and faster as time went on. This force became known as dark energy, a name that reflected both its profound importance and our complete ignorance of its nature. Dark energy reshaped cosmology yet again. It suggested that most of the universe was made of something we could not see, touch, or directly detect. Ordinary matter, Everything from stars and planets to people and galaxies made up only a tiny fraction of the cosmic budget. The rest was dominated by dark matter and dark energy, invisible components that govern the universe's structure and evolution. Still, even with these revelations, cosmologists believed they had a solid framework. The Standard Model of Cosmology successfully explained the cosmic microwave background, the large-scale structure of the universe, and the formation of galaxies. It wasn't perfect, but it worked remarkably well. The expansion rate, though mysterious in its cause, seemed measurable and consistent. Until it wasn't. Over the last decade, astronomers have encountered a troubling inconsistency. When they measure the expansion rate of the universe using the earliest light left over from the Big Bang, they get one answer. When they measure it by observing galaxies and exploding stars in the nearby universe, they get another and. The two do not agree. The difference is not subtle. It is large, persistent, and growing more significant with every improvement in data. This discrepancy has become known as the Hubble Tension, and it represents far more than a technical disagreement. It is a crack in the foundation of modern cosmology. If the universe is expanding faster than our best theories predict, then something fundamental is missing from our understanding of reality. The implications are profound. It could mean that dark energy behaves differently than we think, changing over time instead of remaining constant. It could point to unknown particles or forces that influence the early universe. Or it could suggest that our theory of gravity itself is incomplete on cosmic scales. Each possibility challenges deeply held assumptions and opens the door to new physics. This is where our story begins, not with certainty, but with doubt. The universe, it seems, is once again reminding us that it does not conform to our expectations. The faster than expected expansion is not just a problem to be solved. It is a clue, hinting that the cosmos still holds secrets waiting to be uncovered. In the chapters ahead, we will explore how scientists measure the expansion of the universe, why those measurements disagree, and what it might mean for the ultimate fate of everything that exists. Because if the universe truly is expanding faster than we thought, then we are standing on the edge of a new cosmic revolution, one that may redefine our place in an ever-stretching, ever-mysterious cosmos. At the dawn of the 20th century, the universe appeared timeless and unchanging. To astronomers of the era, the night sky told a simple story. Stars maintained fixed positions relative to one another. Constellations repeated their patterns with clockwork precision, and the heavens seemed immune to the passage of time that shaped life on Earth. This apparent stillness was not merely a poetic impression. It was the foundation upon which early cosmology was built. The prevailing belief was that the universe had always existed in roughly the same form and would continue to do so indefinitely. This assumption was deeply rooted in centuries of observation. Even as telescopes grew more powerful, revealing nebulae, star clusters, and distant points of light, nothing suggested large-scale motion. Astronomers could measure the proper motion of nearby stars. But these movements were small, slow, and easily explained within a static cosmic framework. The idea that the universe itself could change in size, that space could stretch or shrink, was not part of scientific discourse. Space was thought to be a fixed stage upon which cosmic events unfolded, not an active participant in the drama. Philosophical and cultural influences reinforced this view. Since ancient times, the cosmos had been associated with permanence and perfection. In classical thought, the heavens were seen as immutable, governed by laws distinct from the messy, ever-changing world below. Even as science replaced philosophy with observation, remnants of this worldview lingered. A static universe felt intuitively right, aesthetically pleasing, and intellectually satisfying. By the late 19th century, astronomy had become a precision science. Spectroscopy allowed scientists to analyze the composition of stars, while photography enabled detailed mapping of the sky. Yet these advances only strengthened the belief in cosmic stability. Nebulae, cloud-like objects scattered across the heavens, were poorly understood. But most astronomers assumed they were relatively small structures within the Milky Way. The universe, as far as anyone knew, was limited to our own galaxy, surrounded by emptiness. This was the intellectual environment into which Albert Einstein introduced his theory of general relativity in 1915. His equations described gravity, not as a force acting at a distance, but as a curvature of space and time caused by mass and energy. The theory was elegant, powerful, and immediately recognized as a breakthrough. But it carried with it an unsettling implication. A universe governed by general relativity could not remain static. Gravity would cause matter to clump together, leading the universe either to collapse inward or to expand outward. Einstein was deeply troubled by this conclusion. Like most scientists of his time, he believed the universe was stable. To reconcile his equations with this belief, he introduced an additional term, the cosmological constant. This term acted as a kind of anti-gravity, counterbalancing the attractive force of matter and allowing the universe to remain in a delicate equilibrium. Mathematically, the solution worked. Philosophically, it preserved the comforting idea of an eternal, unchanging cosmos. Einstein was not alone in this approach. Other physicists explored similar models, all attempting to describe a universe that neither expanded nor contracted. The possibility of a dynamic universe was considered speculative at best and deeply unsettling at worst. After all, if the universe were expanding, it implied a beginning, a moment in time when everything started. Such a concept felt unscientific, even theological, to many researchers of the era. Meanwhile, observational astronomy was quietly laying the groundwork for a revolution. Using large telescopes, astronomers began measuring the spectra of nebulae, breaking their light into component wavelengths. These spectra revealed patterns that could be compared to known elements, allowing scientists to determine not only composition, but motion. When an object moves away from an observer, its light shifts toward longer, redder wavelengths, a phenomenon known as REDSHI. At first, these red shifts were puzzling. Many nebulae appeared to be moving at extraordinary speeds, far greater than those of stars within the Milky Way. Some astronomers suggested exotic explanations, while others dismissed the measurements as errors. The idea that these objects might be incredibly distant and moving away because the universe itself was expanding not yet gained traction. The situation was further complicated by uncertainty over the nature of the nebulae themselves. Were they nearby clouds of gas or distant galaxies in their own right? This question came to a head in the early 1920s during what became known as the Great Debate, a public disagreement between prominent astronomers over the scale of the universe. At stake was nothing less than the size of reality itself. The debate was resolved not through argument, but through observation. Using powerful telescopes, astronomers identified specific types of stars within certain nebulous stars whose intrinsic brightness was well understood. By comparing their known brightness to how faint they appeared, scientists could calculate their distance. The results were staggering. These nebulae were far beyond the boundaries of the Milky Way. They were galaxies, vast collections of stars separated from us by millions of light years. With this realization, the universe suddenly became incomprehensibly larger, and the redshifts observed in these galaxies took on new meaning. They were not random motions within a static universe. They were signs of large-scale cosmic movement. The final blow to the idea of a static universe came when astronomers noticed a clear pattern. The farther away a galaxy was, the greater its redshift. This relationship was simple, consistent, and impossible to ignore. Space itself was expanding, carrying galaxies along with it. The universe was not standing still. It was growing. Ironically, Einstein initially resisted this conclusion. When confronted with evidence for expansion, he reportedly referred to the cosmological constant as his greatest blunder. In reality, the story is more nuanced, but the sentiment captures the shock felt by the scientific community. A static universe, long taken for granted, had been revealed as an illusion. The shift from a static to an expanding universe was more than a change in scientific models. It was a transformation in how humanity understood existence. If the universe was expanding, then it must have been smaller in the past. If it was smaller in the past, then it had a beginning. Time itself became a cosmic dimension, stretching backward toward an origin point that would later be called the Big Bang. Yet even as the idea of expansion gained acceptance, many questions remained unanswered. What caused the expansion? Would it continue forever, slow down, or reverse? How fast was it happening? These questions would dominate cosmology for the rest of the century. For a time, however, the mystery seemed manageable. Scientists believed that by measuring the expansion rate accurately and refining their models, they could fully describe the universe's evolution. The shock of abandoning a static cosmos gave way to optimism. The universe was dynamic, but it appeared to follow understandable rules. That confidence would not last forever. The assumption of a static universe had fallen. But it had left behind a valuable lesson. The cosmos does not conform to human intuition. Ideas that feel natural and permanent can collapse under the weight of evidence. And as later generations of astronomers would discover, the universe still had surprises waiting. Surprises that would once again challenge the foundations of what we think we know about reality. In the next chapter, we will explore how the discovery of cosmic expansion led to one of the most important laws in astronomy, and how a single number, the expansion rate of the universe, would become both a triumph and a source of profound confusion for modern science. The realization that the universe is expanding did not arrive all at once. It emerged slowly through years of observation, debate, and painstaking measurement. At the center of this transformation was a quiet but revolutionary shift in how astronomers interpreted the light arriving from distant galaxies. What began as faint spectral lines on photographic plates would ultimately redefine the scale, age, and behavior of the entire universe. In the early 20th century, astronomers were still grappling with the true nature of the mysterious nebulae scattered across the sky. These objects appeared as faint, cloudy patches through telescopes, and opinions were deeply divided over what they represented. Some believed they were forming stars within the Milky Way, while others suspected they were distant systems far beyond our galaxy. Without a reliable way to measure cosmic distances, the debate remained unresolved. The breakthrough came with the identification of a special class of stars, known as Cepheid variables. These stars pulse in brightness at regular intervals, and crucially, the period of their pulsation is directly related to their intrinsic luminosity. Once astronomers understood this relationship, Cepheids became powerful cosmic distance markers. By comparing how bright a Cepheid appeared from Earth to how bright it truly was, astronomers could calculate its distance with unprecedented accuracy, using the most powerful telescope of his time. Edwin Hubble began searching for Cepheid variables within nearby nebulae. When he found them, the implications were immediate and staggering. The distances he calculated were far greater than the size of the Milky Way. These nebulae were not clouds of gas. Within our galaxy, they were galaxies themselves. Vast stellar cities, separated from us by millions of light years. This discovery expanded the known universe by orders of magnitude. Humanity's cosmic address suddenly felt insignificant. One galaxy among countless others scattered across an immense and largely empty cosmos. But Hubble's work was far from finished. As astronomers continued to study the spectra of these galaxies, a deeper pattern began to emerge. Spectroscopy revealed that light from distant galaxies was shifted toward longer wavelengths, a phenomenon known as redshift. The most straightforward interpretation of redshift was motion. Galaxies appeared to be moving away from Earth. At first, this seemed puzzling. Why would nearly every galaxy be receding from us? Was Earth somehow positioned at the center of a massive cosmic explosion? Hubble approached the problem systematically. He combined distance measurements from Cepheid variables with redshift data gathered by other astronomers. When he plotted galaxy distance against recession speed, he uncovered a remarkably simple relationship. The farther away a galaxy was, the faster it was moving away. This linear relationship became known as Hubble's law. It provided the first clear observational evidence that the universe itself was expanding. The implications were profound. Space was not merely a passive container holding galaxies in place. It was dynamic, stretching over time and carrying galaxies along with it. Importantly, this expansion did not imply that galaxies were flying through space away from a central point. Instead, space itself was growing. It's increasing the distance between galaxies everywhere at once. This distinction was crucial. In an expanding universe, every observer sees other galaxies moving away, regardless of location. There is no center of expansion, no privileged vantage point. The universe expands uniformly, preserving the principle that no location is special. This realization resolved the troubling implication that Earth might occupy a central cosmic position and aligned perfectly with the philosophical foundations of modern physics. Hubble's law introduced a new fundamental, quantity, into cosmology, the Hubble constant. This number describes the rate at which the universe is expanding today. In simple terms, it tells us how fast galaxies recede from one another per unit of distance. The Hubble constant became a cosmic clock, allowing scientists to estimate how long the universe had been expanding and, by extension, its age. Early estimates of the Hubble constant were crude and uncertain. Initial values suggested a universe much younger than Earth itself, a clear contradiction that signaled errors in distance measurements. Over time, as techniques improved and more reliable data became available, estimates converged toward a more reasonable value. With each refinement, confidence grew that cosmologists were closing in on the true expansion rate of the universe. The concept of cosmic expansion also reshaped theoretical physics. Solutions to Einstein's equations that once seemed abstract or unphysical suddenly gained real-world relevance. Models of an expanding universe, previously dismissed or overlooked, became central to cosmological research. Theoretical predictions and observational data began to reinforce one another, forming a coherent picture of a universe that evolved over time. Perhaps the most transformative implication of Hubble's discovery was the realization that the universe had a beginning. If space is expanding now, then it must have been smaller in the past. Tracing this expansion backward leads to a state of extreme density and temperature. Moment when the universe as we know it emerged. This idea laid the foundation for the Big Bang theory, which would later be supported by multiple independent lines of evidence. Despite its revolutionary nature, Hubble's discovery was met with caution. Some astronomers questioned whether redshift truly indicated motion, or whether alternative explanations might exist. Others debated the reliability of distance measurements. But as data accumulated and methods improved, skepticism gave way to acceptance. The expanding universe became an established fact of science. Yet even as the framework of cosmic expansion solidified, uncertainties remained. The precise value of the Hubble constant continued to be refined, and different measurement techniques produced slightly different results. For decades, these discrepancies were small enough to be attributed to experimental limitations. Few suspected that they might hint at a deeper problem lurking beneath the surface. The success of Hubble's law also masked a subtle complexity. While the universe was expanding, gravity was simultaneously pulling matter together, forming galaxies, clusters, and vast cosmic structures. The expansion was not uniform on small scales. Local regions could collapse even as the universe as a whole grew larger. Understanding this interplay between expansion and gravity became a central challenge for cosmologists. As the 20th century progressed, new tools transformed observational astronomy. Radio telescopes, space-based observatories, and advanced detectors opened new windows onto the cosmos. Each technological leap refined measurements of cosmic expansion and strengthened the prevailing cosmological model. By the late 20th century, scientists believed they had a firm grasp on the universe's behavior. That confidence was reinforced by the discovery of the cosmic microwave background, the faint afterglow of the early universe. Its properties matched theoretical predictions with stunning precision, providing strong support for the Big Bang framework and the expanding universe model. Cosmology appeared to be entering an era of precision science, and yet, hidden within this apparent success was a growing tension. As measurement techniques became more precise, subtle inconsistencies began to emerge. Different methods of measuring the Hubble constant, once thought to converge, started to drift apart. The discrepancies were small at first, easily dismissed as statistical noise. But over time, they grew larger and more persistent. What had once been a triumph of observational astronomy was slowly becoming a puzzle. The very law that revealed the universe's expansion now pointed toward a mystery that could not be ignored. Hubble's legacy, it seemed, was not just the discovery of cosmic expansion, but the opening of a question that modern cosmology is still struggling to answer. In the next part, we will explore how scientists measure the expansion rate of the universe today, why different methods produce conflicting results, and how this disagreement has evolved into one of the most serious challenges facing our understanding of the cosmos. Once the expansion of the universe was firmly established, the next great challenge was precision. Knowing that the universe is expanding was no longer enough. Scientists wanted to know how fast it was expanding and with as much accuracy as possible. The expansion rate would determine the age of the universe, its size, and ultimately its fate. For decades, cosmologists believed this was simply a matter of better instruments and improved measurements. What they did not anticipate was that the universe would offer two different answers to the same question. To measure the expansion rate of the universe, astronomers developed fundamentally different approaches. One looks deep into the early universe, back to a time just a few 100,000 years after the Big Bang. The other examines the nearby universe, using objects close enough to observe in detail. In theory, both methods should converge on the same value for the expansion rate today. In practice, they do not. The first method relies on the cosmic microwave background, or CMB. This ancient radiation is the afterglow of the Big Bang, released when the universe cooled enough for atoms to form, and light could finally travel freely through space. Today, the CMB fills the universe, detectable in every direction as a faint, nearly uniform microwave signal. Embedded within this radiation are tiny fluctuations, minute temperature variations, that encode a wealth of information about the universe's earliest moments. By studying the pattern of these fluctuations, cosmologists can reconstruct the conditions of the early universe with remarkable precision. These measurements reveal the universe's composition, geometry, and initial expansion rate. Using the laws of physics as we understand them, scientists then evolve this early universe forward in time to predict how fast it should be expanding today. This approach produces a value for the Hubble constant that is indirect, but deeply rooted in fundamental physics. The second method takes a more direct route. Instead of looking backward in time, it measures the expansion of the universe as it is happening now. This approach depends on objects known as standard candles, astronomical sources whose true brightness is known. By comparing how bright these objects appear from Earth to how bright they actually are, astronomers can calculate their distance. When those distances are combined with redshift measurements, the expansion rate of the universe can be directly determined. Among the most important, standard candles are Cepheid variable stars in type Ia supernova. Cepheids act as stepping stones, allowing astronomers to measure distances to nearby galaxies. Type Ia supernova, which explode with nearly uniform brightness, extend those measurements much farther, reaching deep into the universe. Together, they form what is known as the cosmic distance ladder. For many years, both methods yielded results that were broadly consistent within experimental uncertainties. Differences existed, but they were small enough to be explained by measurement errors or incomplete data. As observational techniques improved, scientists expected these discrepancies to shrink and eventually disappear. Instead, the opposite happened. As data quality increased, the gap between the two measurements widened. The early universe method consistently produced a lower expansion rate. The late universe method consistently produced a higher one. The difference grew too large to ignore, exceeding the threshold that scientists typically use to claim a statistically significant result. This persistent disagreement became known as the Hubble Tension. The Hubble Tension is not a minor technical issue. It is a profound challenge to the standard model of cosmology. If the early universe measurements are correct, then our understanding of cosmic evolution, accurately predicts today's expansion rate, and the late universe measurements must be flawed. If the late universe measurements are correct, and something is missing from our model of the universe's history, both sides have been scrutinized exhaustively. Astronomers have re-examined calibration techniques, corrected for systematic errors, and refined distance measurements. Space-based telescopes have reduced uncertainties caused by Earth's atmosphere. Independent teams have reproduced results using different instruments and methods. Yet the discrepancy remains. This persistence suggests that the problem may not lie in the measurements, but in the assumptions underlying the model itself. The early universe method assumes that the laws of physics governing the cosmos have remained constant over time. It assumes that dark energy behaves in a specific, unchanging way. It assumes that the contents of the universe are fully accounted for. If any of these assumptions are wrong, the predicted expansion rate would be incorrect. One possibility is that dark energy, the mysterious force driving cosmic acceleration, has evolved over time. In the standard model, dark energy is treated as a constant, unchanging property of space itself. But if dark energy was weaker in the early universe and became stronger later on, it could explain why the universe appears to be expanding faster today than predicted. Another possibility is the existence of unknown particles or forms of energy that influenced the early universe but are no longer detectable. These hypothetical components could have altered the expansion history in subtle ways, leaving an imprint on the cosmic microwave background while affecting the present-day expansion rate. Some scientists have even suggested that our understanding of gravity may be incomplete. Einstein's theory of general relativity has passed every experimental test within the solar system and in many astrophysical contexts, but the Hubble tension raises the possibility that gravity behaves differently on the largest cosmic scales. If true, this would represent a fundamental shift in physics. The tension has also motivated entirely new measurement techniques. Astronomers have begun using gravitational waves ripples in space-time produced by merging black holes and neutron stars as standard sirens to measure cosmic distances independently of traditional methods. Others are using the motion of galaxies within clusters or the bending of light by gravity to infer expansion rates. So far, these approaches have not fully resolved the discrepancy, but they have added weight to the mystery. What makes the Hubble tension particularly unsettling is that both methods are internally consistent. Each tells a coherent story of the universe when considered on its own. The conflict arises only when they are compared. It is as if the universe is offering two reliable narratives that cannot both be true. This situation places cosmology at a crossroads. Either there is an undiscovered systematic error affecting one or both measurement techniques, or the standard model of cosmology, one of the most successful scientific theories ever constructed, is incomplete. Both possibilities are unsettling, but the latter is also thrilling. Throughout the history of science, such discrepancies have often preceded major breakthroughs. The implications extend beyond academic debate. The expansion rate of the universe influences estimates of its age, the formation of cosmic structures, and predictions about its ultimate fate. A faster expansion could mean a younger universe, altered timelines for galaxy formation, and a more dramatic cosmic future as new telescopes and missions come online. Scientists are gathering data with unprecedented precision. Each new measurement adds to the tension rather than relieving it. Far from converging on a single answer, the universe seems to be insisting that we rethink our assumptions. In the next chapter, we will explore why this discrepancy represents a crisis for modern cosmology, and how it may signal the need for new physics that could fundamentally change our understanding of space, time, and the universe itself. At first glance, the disagreement over the universe's expansion rate might sound like an obscure technical problem, something only cosmologists would worry about. A difference of a few kilometers per second per megaparsec hardly feels world-shaking. But beneath those numbers lies a much deeper issue. The Hubble tension is not merely a disagreement between measurements. It is a direct challenge to the framework that underpins our understanding of the universe. It represents a crisis not because scientists lack data, but because the data refuse to agree with one another. modern cosmology is built on a remarkably successful model. It explains how the universe began, how it evolved, and how large-scale structures like galaxies and clusters formed. It accurately predicts the cosmic microwave background, the distribution of matter across vast distances, and the way light bends around massive objects. Few scientific theories have ever been tested so thoroughly or succeeded so convincingly. And yet, the Hubble tension suggests that this model, for all its triumphs, may be incomplete. The seriousness of the problem lies in its persistence. Scientific discrepancies often vanish with better instruments, larger datasets, or more careful analysis. But the Hubble tension has done the opposite. As measurements become more precise, the disagreement grows sharper. Independent teams, using different telescopes, methods, and assumptions, continue to arrive at the same conflicting results. This is the kind of inconsistency that physicists take very seriously, because it suggests the problem is not experimental noise, but a fundamental gap in understanding. At the heart of the crisis is the assumption that the universe's behavior can be described by a single, consistent set of physical laws operating uniformly across time and space. The standard cosmological model assumes that the same rules governing the early universe also apply today. If the early universe predicts one expansion rate and the present universe displays another, then at least one of those assumptions must be wrong. This raises an uncomfortable possibility. Our picture of cosmic history may be flawed. The early universe measurements rely on a detailed understanding of how matter, radiation, and dark energy interacted shortly after the Big Bang. If something unexpected occurred during that period, something not included in current models, it could have altered the universe's expansion in ways that still affect what we observe. Today, one implication is that the universe may contain components we have not yet discovered. These could be new particles, new fields, or entirely new forms of energy. They might have influenced the expansion of the universe early on, leaving behind subtle traces in the cosmic microwave background. While invisible to us now, their effects could still be shaping the universe's evolution. Another possibility is that dark energy, the mysterious force driving cosmic acceleration, is not as simple as we assume. In the standard model, dark energy is treated as a constant property of space, exerting the same influence everywhere and at all times. But what if dark energy changes? What if it grows stronger as the universe ages, or behaves differently at different scales? Such behavior could naturally explain why the expansion appears faster today than predicted from early universe observations. If dark energy is dynamic rather than constant, the implications are profound. It would mean that the universe's fate is far less certain than we thought. Predictions about eternal expansion, cosmic isolation, the ultimate end of star formation would all need to be reconsidered. The universe might not simply drift apart forever. It could evolve in unexpected and dramatic ways, perhaps the most radical. Implication of the Hubble tension is the possibility that our understanding of gravity is incomplete. Einstein's theory of general relativity has been spectacularly successful, but it has never been tested directly on the largest cosmic scales. If gravity behaves differently across vast distances, even by a small amount, it could alter the expansion history of the universe in subtle but measurable ways. Such a discovery would represent a paradigm shift in physics. Gravity is one of the fundamental forces shaping reality, governing everything from falling apples to orbiting planets and collapsing stars. To find that it behaves differently at cosmic scales would open an entirely new frontier in theoretical physics. It would also help explain other mysteries, such as the nature of dark matter and the unification of gravity with quantum mechanics. The crisis deepens because the Hubble tension touches nearly every aspect of cosmology. The expansion rate influences how quickly galaxies form, how matter clumps together, and how light travels through space. A faster expansion rate could mean that galaxies formed earlier than expected, or that structures evolved differently than current models predict. These changes ripple outward, affecting our interpretation of countless observations. The age of the universe is also at stake. A faster expansion implies a younger universe, potentially creating tension with estimates based on the ages of the oldest stars in globular clusters. While current estimates still broadly agree, a significant shift in the expansion rate could force scientists to re-examine long-held assumptions about cosmic timelines. Beyond the technical implications lies a deeper philosophical challenge. Cosmology has long aimed to provide a complete, self-consistent story of the universe from its origin to its ultimate fate. The Hubble tension threatens that narrative. It suggests that our story may be missing key chapters, or that some of the chapters we thought we understood need to be rewritten. This is not the first time science has faced such a crisis. History is filled with moments when observations refuse to fit existing theories. In many cases, these moments mark the beginning of revolutionary advances. The discovery of anomalies in planetary motion led to the development of general relativity. Inconsistencies in atomic spectra gave rise to quantum mechanics. Each time, the resolution required a willingness to abandon comfortable assumptions and embrace new ideas. In this sense, the Hubble tension may be a sign of progress rather than failure. It indicates that cosmology has reached a level of precision, where subtle cracks in the theoretical framework are becoming visible. These cracks are opportunities, clues pointing toward deeper truths about the universe. The scientific community is responding with urgency and creativity. New observational campaigns are underway, using next-generation telescopes and novel techniques to probe cosmic expansion with unprecedented accuracy. Theoretical physicists are exploring bold ideas, from evolving dark energy to modified gravity and beyond. Each proposed solution is tested rigorously against data, pushing the boundaries of what we know, yet for now, the crisis remains unresolved. The universe is expanding faster than expected, and no single explanation has emerged as definitive. This uncertainty is unsettling, but it is also exhilarating. It reminds us that the universe is not a solved puzzle, but a living mystery one that continues to challenge, surprise, and inspire. In the next part, we will dive deeper into dark energy, the leading suspect in this cosmic mystery, and explore how its unknown nature may hold the key to understanding why the universe's expansion refuses to conform to our expectations. If there is one concept that dominates modern cosmology with both its clarity and mystery, it is dark energy. Invisible, intangible, and profoundly influential, dark energy is believed to make up roughly 70% of the universe. It neither emits nor absorbs light, yet it governs the large-scale behavior of space itself. When scientists confront the question of why the universe appears to be expanding faster than expected, dark energy stands out as the most likely and most enigmatic explanation. The existence of dark energy was not predicted by theory. It was discovered by accident. In the late 1990s, astronomers set out to measure how the expansion of the universe was slowing down under the influence of gravity. The assumption seemed reasonable. Gravity pulls matter together, so over time it should act as a brake on cosmic expansion. But when researchers analyzed distant supernova stellar explosions, so bright they can be seen across billions of light years, they found something astonishing. The universe was not slowing down. It was accelerating. This acceleration required a new explanation. Something was counteracting gravity on the largest scales, pushing galaxies apart with increasing strength. Scientists called this unknown influence dark energy, not because it is literally dark, but because its nature remains hidden. The name itself reflects our ignorance. We know dark energy exists because of what it does, not because of what it is, in the standard cosmological model. Dark energy is treated as a cosmological constant, a uniform energy density inherent to space itself. As the universe expands, more space is created, and with it, more dark energy. This leads to an ever-increasing push that accelerates expansion over time. The idea fits observations remarkably well and provides a simple explanation for cosmic acceleration. However, simplicity can be deceptive. The cosmological constant raises profound theoretical problems. When physicists attempt to calculate its value using quantum field theory, the result is wildly inconsistent with observations off by a factor of more than 100 orders of magnitude. This discrepancy is one of the largest known in theoretical physics. suggesting that something fundamental is missing from our understanding despite these issues. The cosmological constant remained the leading explanation because it worked. It explained the data, predicted observations accurately, and fit neatly into existing models. For years, there was little reason to question it. But the emergence of the Hubble tension has forced scientists to reconsider whether this picture is truly complete. If dark energy is responsible for the accelerated expansion of the universe, then its properties directly influence the expansion rate. A small change in how dark energy behaves could have significant consequences for cosmic history. This has led researchers to ask a critical question: what if dark energy is not constant? One possibility is that dark energy evolves over time. In this scenario, dark energy may have been weaker in the early universe and grown stronger as the universe aged. Such behavior could reconcile the conflicting expansion rates measured from the early universe and the present day. Early universe observations would reflect a slower expansion, while late-time measurements would capture the stronger influence of dark energy. Theoretical models of evolving dark energy often involve scalar fields entities that assign a value to every point in space and time. These fields could change gradually, influencing the expansion rate in subtle ways. While such models are mathematically complex, they offer a tantalizing way to resolve the Hubble tension without abandoning the broader framework of cosmology. Another possibility is that dark energy interacts with other components of the universe, such as dark matter. In the standard model, dark energy and dark matter are treated as independent entities, influencing the universe in different ways. But if they interact, even weakly, the consequences could be significant. Energy transfer between these components could alter the expansion history, leading to the observed discrepancy. These ideas remain speculative, but they highlight how little we truly know about the dominant force shaping the universe. Dark energy is not something we can study in a laboratory. Its effects are only visible on cosmic scales, making it one of the most challenging subjects in all of science. The implications of dynamic dark energy extend beyond the Hubble tension. If dark energy changes over time, the ultimate fate of the universe becomes uncertain. A constant dark energy leads to a future where galaxies drift apart, star formation dwindles, and the universe becomes cold and empty. But evolving dark energy could produce very different outcomes, including dramatic scenarios in which cosmic expansion becomes violently disruptive. 1. Such possibility is the Big Rip, hypothetical future where dark energy grows so strong that it eventually overcomes all other forces. Galaxies would be torn apart, stars ripped from their orbits, planets shredded, and even atoms themselves pulled apart. While this remains speculative, the fact that it is seriously considered underscores how deeply dark energy influences cosmic destiny. At the same time, dark energy could also weaken in the future. If its strength diminishes, cosmic expansion could slow or even reverse, leading to a potential cosmic collapse. Such scenarios challenge the notion of an inevitable, unchanging cosmic trajectory and remind us that the universe's future is still an open question. The search for clues about dark energy is one of the central goals of modern astronomy. Large-scale surveys are mapping the distribution of galaxies across billions of light-years, looking for subtle patterns that reveal how expansion has changed over time. Space-based telescopes are measuring distant supernova with unprecedented precision, while gravitational lensing studies probe the influence of dark energy on the curvature of space. Each new dataset adds to the picture, but none have yet delivered a definitive answer. Dark energy remains stubbornly elusive, revealing itself only through its gravitational effects. The Hubble tension has sharpened the focus on this mystery, turning dark energy from a theoretical curiosity into a central problem in cosmology. There is also a deeper, philosophical dimension to the dark energy puzzle. For centuries, science has advanced by uncovering hidden structures beneath apparent simplicity. The discovery that most of the universe consists of unknown components challenges our sense of understanding and humility. It suggests that our familiar world of stars and galaxies is only a small part of a much larger, more complex reality. dark energy forces us to confront the limits of human knowledge. It reminds us that even with our most powerful instruments and sophisticated theories, the universe can still defy explanation. Yet it also motivates exploration. Every unanswered question drives innovation, collaboration, and creativity in science. As researchers continue to investigate dark energy, they do so with the awareness that resolving its nature could revolutionize physics. It could reveal new fields, new symmetries, or entirely new principles governing reality. The stakes are enormous, not just for cosmology, but for our understanding of space, time, and existence itself in the next chapter. We will explore alternative explanations beyond dark energy ideas that challenge conventional thinking and propose that the universe's accelerated expansion may be signaling the presence of entirely new physics. As the Hubble tension refused to fade, some scientists began to consider a more radical possibility. What if the problem is not dark energy at all, but the very foundations of our physical theories? Throughout the history of science, moments like this, when observations stubbornly contradict predictions, have often signaled the need for new physics. The expanding universe may now be delivering such a message, hinting that our current understanding of reality is incomplete. The standard model of cosmology rests on a relatively small set of assumptions. It assumes that the laws of physics are the same everywhere and at all times. It assumes that gravity behaves according to Einstein's theory of general relativity on all scales. And it assumes that the contents of the universe, ordinary matter, dark matter, radiation, and dark energy, are fully accounted for. If any one of these assumptions is wrong, even slightly, the universe's expansion history could change in measurable ways. One class of proposed solutions involves introducing new forms of matter or energy that existed in the early universe but faded away over time. These hypothetical components could have briefly altered the expansion rate shortly after the Big Bang, leaving behind a lasting imprint that affects today's measurements. Because they no longer play a major role, they would be difficult to detect directly, making them invisible to current observations, except through their indirect effects. Among the most discussed ideas is the concept of early dark energy, like the dark energy that dominates the universe today. Early dark energy would have exerted a significant influence only during the universe's infancy. By increasing the expansion rate during this critical period, it could reconcile the discrepancy between early and late universe measurements without requiring dark energy to change dramatically at later times. While intriguing, models of early dark energy must carefully match observational data, and so far, none have emerged as definitive. Another possibility involves new particles. Beyond those described in the standard model of particle physics, these particles might have contributed additional energy density in the early universe, subtly altering its expansion. Some theories propose the existence of extra neutrino-like particles or other exotic species that interact very weakly with ordinary matter. Even a small contribution from such particles could have measurable consequences on cosmic scales. The idea of unknown particles is not as far-fetched as it might seem. The standard model of particle physics, while extraordinarily successful, is known to be incomplete. It does not account for dark matter, gravity, or the observed imbalance between matter and antimatter in the universe. The Hubble tension could be another clue pointing toward physics beyond the standard model, linking cosmology and particle physics in unexpected ways. Perhaps the most provocative proposals involve modifications to gravity itself. Einstein's theory of general relativity has passed every experimental test within the solar system and many astrophysical environments. However, it has never been tested directly across the vast distances separating galaxies and clusters. If gravity behaves differently on these scales, even by a tiny amount, the cumulative effect over billions of years could alter the universe's expansion rate. Modified gravity theories attempt to extend or revise general relativity to account for cosmic observations without invoking dark energy. Some models introduce additional fields that modify how gravity operates at large distances. Others propose extra dimensions of space that influence gravitational behavior in subtle ways. While many of these ideas are mathematically elegant, they must confront stringent observational constraints, making them difficult to implement successfully. Extra dimensions, once confined to the realm of science fiction, are taken seriously in certain theoretical frameworks. In these models, the universe we observe exists within a higher dimensional space, with gravity leaking into dimensions we cannot directly perceive. Such leakage could weaken gravity on large scales, effectively accelerating cosmic expansion. Although speculative, these ideas arise naturally in attempts to unify gravity with quantum mechanics. Quantum effects themselves may also play a role. The early universe was governed by physics at energy scales far beyond anything achievable in laboratories today. Quantum fluctuations during that era could have influenced cosmic expansion in ways that standard models do not fully capture. Some researchers suggest that remnants of these effects may still be visible in the Hubble Tension. Another avenue of exploration involves questioning the assumption that the universe is perfectly homogeneous and isotropic on large scales. While this assumption has strong observational support, small deviations could have significant consequences for expansion measurements. If the universe has subtle large-scale structures or variations, they could bias observations in ways that mimic an accelerated expansion. These ideas remain controversial, as they challenge deeply held principles of cosmology. Yet they illustrate the lengths to which scientists are willing to go to resolve the Hubble tension. When a problem resists conventional solutions, unconventional thinking becomes necessary. Importantly, the search for new physics is guided by data, not speculation alone. Every proposed model must make testable predictions and survive rigorous comparison with observations. Many ideas have already been ruled out, while others remain viable but unproven. This process of elimination is slow and painstaking, but it is the hallmark of scientific progress. The tension has also sparked innovation in observational techniques. New methods of measuring cosmic expansion are being developed to provide independent checks on existing results. Gravitational waves, for example, offer a completely different way to measure distances in the universe, free from many of the uncertainties affecting traditional methods. These standard sirens could play a crucial role in determining whether new physics is truly required. What makes this moment in cosmology particularly exciting is the sense that multiple fields of physics are converging on the same mystery. Particle physicists, astrophysicists, and cosmologists are all grappling with questions that intersect at the Hubble tension. This convergence increases the likelihood that its resolution will have far-reaching implications, potentially reshaping our understanding of the universe at the most fundamental level. At the same time, humility is essential. The history of science is filled with examples where apparent crises were resolved through improved understanding of existing theories rather than radical new ones. It is possible that subtle, systematic errors or overlooked complexities still lurk within current measurements. The challenge lies in distinguishing between a genuine signal of new physics and an artifact of observation, regardless of the outcome. The exploration itself is transformative. The Hubble tension has reinvigorated cosmology, pushing it beyond incremental refinement and into a period of deep questioning. It has reminded scientists that even well-established theories must remain open to revision when confronted with compelling evidence. As we move forward, the universe continues to serve as both laboratory and teacher. Its expansion, seemingly faster than we can explain, challenges us to look beyond familiar ideas and consider new possibilities. Whether the answer lies in dark energy, new particles, modified gravity, or something entirely unexpected. The journey toward understanding promises to expand not only our knowledge of the cosmos, but our conception of reality itself. In the next chapter, we will explore how a faster expansion rate could shape the future of the universe and what it might mean for the ultimate fate of galaxies, stars, and everything that exists. The question of how fast the universe is expanding is not merely a technical detail. It is a key that unlocks the future of everything that exists. The expansion rate determines how galaxies evolve, how stars form, and how cosmic structures change over time. If the universe is expanding faster than we thought, then the future of the cosmos may look very different from the one scientists once confidently predicted for much of the 20th century. Cosmologists debated whether the universe would expand forever or eventually collapse under the pull of gravity. The answer depended on the amount of matter in the universe and the strength of gravitational attraction. If gravity dominated, expansion would slow, stop, and reverse, leading to a big crunch. If not, the universe would expand indefinitely. Growing colder and more dilute over time, the discovery of cosmic acceleration dramatically altered this picture. Dark energy, by overpowering gravity on large scales, appeared to guarantee eternal expansion. Galaxies would drift farther apart, star formation would gradually decline, and the universe would fade into a long, quiet future, often described as the heat death of the cosmos. This scenario became the prevailing view: calm, gradual, predictable. But a faster-than-expected expansion rate complicates this narrative. If cosmic expansion is accelerating more rapidly than current models predict, the long-term fate of the universe could be far more extreme. Small differences in the expansion rate today can lead to enormous differences over billions or trillions of years. In cosmology, tiny changes echo across eternity. One of the most significant consequences of faster expansion is the increasing isolation of galaxies. As space stretches more quickly, galaxies move beyond each other's observable horizons at an accelerated pace. Eventually, distant galaxies will fade from view entirely, their light stretched beyond detectability. Future observers, living in far-off epochs, may see only their own galaxy and its nearest neighbors, unaware that a vast universe ever existed beyond. This cosmic isolation has profound implications for astronomy itself. The evidence that allowed us to reconstruct the history of the universe, the cosmic microwave background. Distant galaxies and large-scale structures will gradually disappear. Knowledge of the Big Bang, cosmic expansion, and the universe's true scale may become inaccessible to future civilizations. Locked away by the relentless stretching of space, a faster expansion also affects the life cycle of galaxies. Galaxies grow and evolve by merging with others and accreting gas from their surroundings. As expansion accelerates, these interactions become less frequent. Gas reservoirs thin out, star formation slows, and galaxies gradually age. The universe becomes dominated by lived, dim stars and stellar remnants. Over time, the cosmic web, the vast network of filaments and voids that defines large-scale structure, will unravel. Clusters of galaxies will remain bound by gravity, but they will become isolated islands in an ever-expanding sea of empty space. Between them, darkness will grow deeper and more profound. In more extreme scenarios, a rapidly accelerating universe could lead to a dramatic and violent end, known as the Big Rip. In this hypothetical future, dark energy becomes so powerful that it overwhelms all other forces. First, galaxy clusters would be torn apart. Then, individual galaxies would be shredded as stars are pulled from their orbits. Eventually, even solar systems, planets, and atoms themselves could be ripped apart by the expansion of space. The Big Rip remains speculative, but it highlights the sensitivity of cosmic fate to the properties of dark energy. If dark energy strengthens over time, even slightly, it could fundamentally alter the destiny of the universe. The difference between a gentle fading and a catastrophic end lies in the details of a force we barely understand. Conversely, faster expansion does not necessarily mean a more destructive future. If dark energy evolves in a complex way, growing stronger now but weakening later, the universe's expansion could slow again in the distant future. Such behavior could lead to entirely different outcomes, including a renewed era of structure, formation, or even a future contraction. The possibility of an unexpected, cosmic turnaround challenges the notion that the universe's future is already written. It reminds us that our predictions are only as good as our understanding of the forces at work. As long as dark energy remains mysterious, the universe's ultimate fate remains uncertain, beyond grand cosmic endings. The expansion rate also influences more subtle aspects of cosmic evolution. The timing of star formation, the growth of supermassive black holes, and the chemical enrichment of galaxies all depend on how quickly the universe expands. A faster expansion could shift these timelines, altering the conditions under which planets and, potentially, life emerge. Some researchers have even speculated that cosmic expansion could influence the long-term prospects for life itself. In a rapidly expanding universe, the window for life to arise and evolve may be shorter. Resources become scarce sooner, and cosmic environments grow harsher more quickly. While highly speculative, such ideas underscore how deeply cosmology is intertwined with questions about existence and meaning. The faster expansion also forces scientists to reconsider the age of the universe. While current estimates remain consistent within uncertainties, a significantly higher expansion rate could imply a slightly younger universe. This would require reconciling cosmological models with observations of the oldest stars and stellar systems, pushing astrophysics toward greater precision and deeper understanding. Importantly, the future of the universe is not determined by expansion alone. Local gravity continues to shape galaxies, stars, and planets. Even in a rapidly expanding cosmos, bound systems remain intact for immense periods of time. Life, if it arises, can persist long after cosmic expansion has rendered the universe vast and empty. What changes most dramatically is the cosmic context. A faster expansion accelerates the transition from a universe rich in interactions to one defined by isolation. The grand, interconnected cosmos we observe today is a temporary phase in a much longer story. Understanding how long that phase lasts and how it ends depends on resolving the mystery of the universe's expansion. In this sense, the Hubble tension is not just a scientific puzzle. It is a question about our cosmic future. It challenges us to refine our models, improve our measurements, and confront the limits of our knowledge. It reminds us that the universe is not static, not settled, not fully understood. As we look ahead, the universe continues to expand, carrying galaxies, stars, and possibilities with it. Whether that expansion leads to a quiet fading, a dramatic tearing apart, or something entirely unexpected remains unknown. What is certain is that the answer will reshape our understanding of the cosmos and our place within it. In the final chapter, we will bring together everything we have explored and reflect on what it means to live in a universe that is still revealing its deepest secrets, expanding not only in size, but in mystery. For centuries, humanity has looked to the night sky seeking certainty. The stars appeared fixed, the heavens orderly, and the universe governed by timeless rules. Each scientific advance seemed to bring us closer to a complete understanding of reality. A final theory that would explain how everything began, how it evolved, and how it would end. Yet the story of cosmic expansion reminds us of a deeper truth. The universe does not reveal itself all at once, and every answer uncovers new questions. The realization that the universe is expanding faster than we thought is not just a correction to a number. It is a profound challenge to our understanding of existence. It tells us that even our most successful theories may be incomplete, that the cosmos still holds surprises capable of reshaping the foundations of science. What once appeared settled is now open to reinterpretation, inviting us to look deeper and think more boldly. At the heart of this mystery lies the tension between observation and theory. On one hand, we have extraordinarily precise measurements of the early universe, preserved in the cosmic microwave background like a fossil record of creation. On the other, we have equally meticulous observations of the universe as it exists today, measured through stars, galaxies, and cosmic explosions. That these two perspectives disagree is not a failure of science. It is science at its most powerful. Disagreement is the engine of discovery. The Hubble tension has transformed cosmology from a field of refinement into one of exploration. It has shifted the focus from fine-tuning known parameters to questioning foundational assumptions. Is dark energy truly constant? Are there unknown particles or forces shaping the cosmos? Does gravity behave differently across vast distances? Each of these questions carries implications that reach far beyond cosmology. Touching the deepest laws that govern reality, This moment echoes pivotal turning points in scientific history, when astronomers discovered that planets did not move exactly as Newtonian physics predicted. It led to the development of general relativity. When classical physics failed to explain atomic behavior, quantum mechanics emerged. In each case, anomalies were not dismissed. They were embraced as clues pointing toward deeper truths. The faster-than-expected expansion of the universe may represent a similar turning point. What makes this mystery particularly compelling is its scale. The forces involved shape the entire universe, influencing the formation of galaxies. It's the evolution of stars and the ultimate fate of everything that exists. Few scientific questions carry such sweeping consequences. Understanding cosmic expansion is not merely about distant galaxies. It is about the past, present, and future of reality itself. Yet, there is also humility in this uncertainty. The realization that 70% of the universe is composed of something we do not understand is a reminder of how small our island of knowledge truly is. It challenges the notion that human understanding is nearing completion and reinforces the idea that exploration is an ongoing journey. It's not a destination. At the same time, there is profound optimism. The tools available to modern science are more powerful than ever before. New telescopes, gravitational wave observatories, and cosmic surveys are poised to deliver data of unprecedented precision. Each new observation has the potential to sharpen the mystery or to reveal the breakthrough that finally resolves it. Either outcome moves science forward. The universe's accelerated expansion also invites reflection beyond physics. It raises questions about time, impermanence, and our place in an ever-changing cosmos. The galaxies we see today are temporary companions in a universe that will one day grow vast and quiet. Yet in this fleeting moment, conscious beings exist who can observe, question, and seek understanding. That alone is extraordinary. As scientists continue to probe the mystery of cosmic expansion, they do so with the awareness that the universe is not obligated to conform to our expectations. Nature follows its own rules, and our task is to uncover them, no matter how surprising they may be. The faster expansion may be telling us that reality is richer, more complex, and more subtle than we have imagined. In the end, the story of the expanding universe is a reminder of why science matters. It is not about final answers, but about the pursuit of understanding. It is about curiosity, resilience, and the willingness to confront the unknown. The universe is still expanding, still evolving, and still revealing its secrets one discrepancy, one discovery, and one insight at a time. And as we stand on this threshold of uncertainty, one thing is clear: the universe is far from finished teaching us who we are and where we come from. Its expansion continues, and with it, our quest to comprehend the vast, mysterious cosmos we call home.